Super. And you don't mind taking questions today, of course.
No, no, of course not. And I just wanted to add the idea that we could do some questions later as well.
Absolutely. If members who can't join us today,
Yeah.
they could send questions in, which would be great. Um, okay, we just gone past the hour here. Um, I would like to introduce to our members here, Richard Godfrey. Um, Richard lives near Frankfurt in Germany, although he has spent time living in, I think you said Somerset in England, that sort of stuff. He's an aerospace engineer, and he can talk a little bit more about all of that sort of stuff when he gets on the mic here. Um, and he's worked on planes. He knows planes. He knows commercial planes. He worked on 747, I understand, and fighter jets like the F-16. So he's extremely knowledgeable, and I personally am very interested in, how did how did Richard come up with the idea of using the weak signal propagation reporter? What's in his background? That's a mystery to me. Anyways, welcome, Richard. It's great to have you
Well,
here, and this is a really a unique opportunity to find out what's happening in the search for MH370. Over to you.
well, thank you, Glenn, for those kind words. And yeah, what got me into Whisper was a radio amateur by the name of Dr. Robert Westphal. And he gave a talk at a Ham Sci conference uh, going back a few years now, and suggested the idea that we could use the Whisper data from the WhisperNet database to track aircraft like MH370. So it wasn't my idea, but I picked up on it. I'm actually not a radio amateur. I'm interested in physics and therefore interested in any kind of scientific investigation. I was actually booked on Air France 447 from Rio to Paris with an onward connection to Frankfurt, and that crashed in the Atlantic in 2009.
Wow.
I fortunately had to stay on business in Brazil another 2 weeks, and I rebooked on a direct flight from Sao Paulo to Frankfurt, where I live, on Lufthansa. But I thought, there, but for the grace of God, go I.
Hmm.
And when MH370 happened, I saw the immediate parallel, an aircraft disappearing in this time, the Indian Ocean, not the Atlantic Ocean, but there were several parallels between Air France 447 and MH370. So that's what got me interested in Whisper and in MH370.
Well, that's great. Thanks. So, at a conference, you find out about Whisper, and you're now using it in the search for 370.
Yeah, well, I first of all was skeptical that Whisper could detect or track aircraft. So I looked into it for myself, and after a while, I found, hey, there's something to this. And so, what I'd like to do today is give you guys a bit of background about MH370 and a bit of background about Whisper and what I believe it can do and what it can't do. And very happy to take your questions. And I'm quite happy to take the questions interactively. So you don't have to wait till the end. If you have a question, then just let us know, and we'll hand over the mic to you. So the title slide I've got up is a picture of the aircraft 9M MRO, a Boeing 777 from Malaysia Airlines, which conducted the flight, MH370. And its initial path was from Malaysia, from Kuala Lumpur International Airport. If you follow the black dots, they are confirmed ADS-B data or civilian radar data or SATCOM ACARS data. So we know exactly where it was headed, and it was according to flight plan and going off towards Vietnam. Then something very strange happened. The transponder was switched off. The radar screens went dark. And it turned out from civilian radar that the aircraft did an almost 180-degree turn back across Malaysia towards Penang Airport. And you'll see we start picking it up. The red dots are the Wspr data. So it went past Penang Airport and up the Strait of Malacca and headed towards the Andaman Islands, a waypoint right at the top there, Igogu. And then it turned again down into the Indian Ocean. So there were three major turns, one at the diversion point, one around Penang, and then another one down into the Indian Ocean. And that was, of course, a complete diversion from the flight plan and very strange behavior. The satellite system from Inmarsat picked up MH370, and it could work out how far MH370 was from the satellite position over the Indian Ocean, and it could work out the relative speed between the satellite and the aircraft. And there are so-called arcs. We start at 1825, then almost every hour, 1941, 2041, all the way down to 0011, and the last arc at 019. So the 8th of March, the next day, just beyond midnight. And these arcs get progressively further down into the Indian Ocean. So we know that the aircraft was somewhere along those arcs at each of those points in time. Gives us a clue, but it doesn't actually tell us the location.
I have a question, Richard.
Sure,
Could you go back to the last slide, please?
sure.
So I assumed it's you that have plotted, that has plotted the Wspr dots there, the red ones. Is that correct?
That's correct.
Okay, I just wanted to make certain because, yeah, okay, that made sense to me. Okay, thank you.
Good, good. So we have the Inmarsat data. We have one other very important fact, and that is we know how much fuel was on board this Boeing 777. So we know exactly how far and how long it can stay in the air with that amount of fuel. And the yellow line is the fuel range, and the magenta line is the seventh arc, and they cross at a point around between 30 and 40 degrees south, around 36 somewhere. So the first place we looked was around 36 degrees south. It took, however, quite a while before we started looking in the Indian Ocean, because we first looked up in the South China Sea and then in the Strait of Malacca and around the Andaman Islands. So it was 10 days later they actually started the aerial search. And they covered a lot of ground in the surface search. A lot of ships, a lot of aircraft involved. There were actually 345 different flights out of Perth in Australia into these various areas marked on the map. And they're around 2,000 kilometers away from Perth. So it took a long while to get to the search area and a long while back. And they could spend, on average, about 4 hours on station having a look. They found some debris or spotted some debris from the aircraft. But by the time the ships got there, they recovered only a few items, and it turned out mostly to be fishing nets or rubbish that had been thrown overboard from passing ships. So that drew a blank, even though they spent 42 days and a lot of money looking for MH370. The next slide, I wanted to ask you guys. I mean, the first question is the fundamental question of all radio amateurs. What is a radio signal? And everybody knows it's electromagnetic wave, and it has certain electrical properties, which we measure in things like volts per meter. And it has several magnetic properties we measure in Teslas, for example. But the next question is a trick question for you guys. Who sent the first radio signal? Does anybody know?
Hertz. Heinrich Hertz.
Well, I would agree with you. It was Heinrich Hertz, but some people say, yeah, his spark gap transmitter was a radio signal and he proved electromagnetic waves exist. But it didn't actually use that signal to communicate information. So people turn Heinrich Hertz down on that basis. Then some say the first person to do a radio signal with information being transmitted was Guglielmo Marconi. But, there are different opinions on that score. Next question, who discovered the ionosphere?
Oh, Heaviside, Oliver.
Exactly. But interestingly, Marconi used the ionosphere before it was discovered or confirmed, later confirmed by Sir Edward Appleton, 1927. But as you point out, it was from Heaviside and much earlier than the proof by Sir Edward Appleton. But Marconi didn't wait for proof or even the postulate that it existed. He discovered it and used it back in 1901, if I remember correctly. Then the next trick question, who invented radar?
Well, I suppose most people would say Watson Watt, but that's probably a trick question. So somebody else.
It's not Watson Watt. He was the first one to demonstrate radar to pick up an aircraft. But before they picked up aircraft, they picked up ships. And there was a guy called Christian Hulsmeyer who invented a system called the telemobiloscope, which used radio waves and bounced them off the metal hull of a ship as it passed Cologne on the Rhine River in Germany. And he patented this telemobiloscope and is considered, in terms of ship radar, as the father of radar, and that's back in 1904. So all I'm doing by asking these trick questions, a bit nasty of me really to do so, is to point out the next slide that there are a long list of scientists, and we today use their units of measurement, Pascal, a Newton, a Fahrenheit, a Celsius, a watt, a volt, an ampere, an ohm. But actually, these are all guys who did something. And without all of these people, down at the bottom of the list, you'll find Nikola Tesla or Heinrich Hertz. And without these people, we would be nowhere with radio science and using what they have found. Now, the next picture I've got is of Professor Joe Taylor, yet another Nobel Prize winner, and the previous list had several Nobel Prize winners. This is when he visited us in Germany, and he's standing next to a friend of mine, Christian Enzfellner, who is the chairman of the Radio Amateur Society of Germany, and has kindly invited me to the 75th anniversary meeting and conference to speak on Wspr. So Joe Taylor invented the Wspr protocol.
Joe is on the left or right?
Joe is the guy on the left.
Okay.
And Christian is the guy with the nice bright blue tie.
Right.
On the right. Joe Taylor says Wspr cannot be used, and it was never designed to be used, to detect or track an aircraft. So I respect his view, but I have a different view. And we're in the process of scientifically proving that Wspr can be used to detect and track aircrafts. So all respect to Joe Taylor. And again, without his Wspr protocol, I wouldn't have the data that I need, and I wouldn't have the WhisperNet database. So I'd be nowhere, frankly. So the WhisperNet database has meanwhile archived last year 2 billion Wspr signals, just in 2024. There are millions added every day. And of those 2 billion last year, 370 million had a propagation distance over 10,000 kilometers. So they go a long way. And 400,000 of those signals were sent with a transmission power less than 1 milliwatt. Now, I guess most of you guys transmit, I don't know, 1 watt or 5 watts. There are people transmitting out there with huge and powerful systems. The NASA Voyager is probably, the Voyager 1 and Voyager 2, probably the most distant man-made objects that we've sent off into space. They're around 20 billion kilometers from Earth at the moment, and they're still continuously transmitting data. Originally, they started off at 21.6 kilobits per second. That was back in 1977. It's now decreased to about 160 bits per second. And by 2050, it'll be down to 40 bits per second. But they still expect to be able to recover the signal from the noise. Wspr, thanks to Professor Joe Taylor's protocol, has a bit rate of 1.4648 bits per second. So give you an idea that that works quite well over very long distances. Are you guys familiar with aircraft scatter experiments, where you use a radio signal and let an aircraft scatter it and see what happens?
I can't say I do.
Okay. Well, let me try an experiment. I'm going to come out of my presentation and go into YouTube. So this is a screen with a map showing an aircraft flying from Corsica in the Mediterranean up to Paris in France. And this line, the red line, is a signal from a radio station down in Marseille to a listener in the French Alps. And normally, the listener can't hear this radio station because there are mountains in the way going up to 2,600 meters in height. And on the right, we got the usual display of the radio signals. So I'm going to try and run this. And to start with, you need to watch this aircraft. You will only hear noise. But as the aircraft actually crosses the path of the signal, you will then hear the music from the station. So if it's a bit loud, the noise, then turn your volume down. If you can't hear the volume, then what I'll do is send you the link to the YouTube video, and then you can watch it yourself. So I'm going to just try it, and you tell me if you can hear the noise.
Oh, yeah.
Yeah?
Yes.
Good. So I'm going to let it run and watch this aircraft cross the propagation path. Sorry about the noise, but I think it comes across quite a clear message to be had there. So let's go back to the presentation. So
Question if I may.
By all means.
Yeah, the radio station, was that on 94 megahertz or something?
94.2 megahertz.
Okay. Yeah,
an FM radio station with a huge transmitter sitting on top of a hill outside of Marseille. But the gag is there are mountains in the way, and normally in the Alps you can't hear it, except if an aircraft goes overhead, and then you can. I mean, a lot of people who live near airports will complain about their television or radio being interrupted when an aircraft comes into land. This is a similar sort of experiment, really.
Okay, thanks.
Free coffee to anyone who can guess what the music was.
Yeah, bit of strong stuff at early or late in the morning for you guys. So there is one kind of radar that uses ionospheric propagation called the over-the-horizon radar. There's a picture of transmitter. Now, there's a set of antenna that go all the way to the horizon. And if you look carefully, the ground has got a copper wire mesh for acres and acres of copper wire. I don't know how many tons of copper wire they used, and it was very expensive, but they made sure they had a very good copper wire mesh ground plane underneath all of these antenna. But they can stretch 3,000 kilometers and look over the horizon and detect aircraft and ships. And there's one in this one is in Australia. And with this system, you can watch a small Cessna aircraft taking off from Singapore airport. And a friend of mine actually worked on this system. So if you've got a big, powerful transmitter, you can look over the horizon, and there are plenty of over-the-horizon radar systems. The Chinese have got them, the Russians have got them, Americans, of course, were the pioneers. Canadians will soon have an over-the-horizon radar, which they bought from the Australians, and to look and watch Russia and China over the Arctic. So it's an interesting system. Wspr uses ionospheric propagation. So we use all the data we can get from the WhisperNet database. In this case, we're tracking MH370 at 2242 UTC. By that time, it's well down in the Indian Ocean. We have satellite data that I mentioned earlier, which tells us sort of a line, the black line of the fifth arc where the aircraft is. But we also have Wspr data. So we have a transmitter NTNOM call sign, receiver in Greenland, OX3XR, picking up that signal. We have a transmitter in the UK, G3JKF, and a receiver, DK6UG in Germany, picking up that signal. And these signals go all the way to the aircraft and come back, get reflected back. And we can pick up the anomalies, both in the signal level and in the signal frequency. So there's a level shift and a Doppler shift, both of which can cause anomalies. And when we zoom in to the location of MH370 of that point in time, we get an intersection of these anomalous signals. And lo and behold, they also line up with the Inmarsat satellite data, which is a completely separate system. And when you get 3 points lining up like that, then you pay attention, because there must have been something which caused those anomalies to happen. And we look at in this case, we got the signal level, the SNR changes, the noise floor. We can calculate at different locations, and it depends, of course, on the location and the background noise in that location, and it depends on the antenna used. Sometimes radio amateurs tell you a lot about what antenna they use for both transmission and reception on different bands. Sometimes they keep that info a little bit secret, but the WhisperNet database does give us the signal to noise ratio, gives us the frequency drift of each signal, and we can track that over time. So we know over a couple of hours how the signal changes between a particular transmitter and a particular receiver. and we can work out what the mean signal to noise ratio is, and what the standard deviation might be. And then we can see if there are any points in time where the signal is outside that standard deviation. And sometimes we've seen signals that are 200% or 300% away from the mean level. Now, the ionosphere is a dynamic environment and will cause all kinds of dynamic fluctuations. But the WhisperNet protocol is a digital protocol, and it tells us over 110.6 seconds that the signal was actually received and decoded and reported in the database. So we get quite a bit of interesting information. And some radio amateurs using Wspr send multiple signals, multiple frequencies, and some even from multiple locations. And we learn a lot about how those signals are received at many other different locations around the world. Radar systems that you find in an airport, for example, are usually what they call monostatic. So the transmitter and the receiver are in the same location. Sometimes you get bistatic radar systems, so the transmitter is separated from the receiver by a certain distance. Wspr is multistatic. There are hundreds of transmitters and hundreds of receivers. So you get a much better pattern, and they are multi-frequency, not just multi-static. So you get very interesting information on different frequency bands. And as you guys well know, there are different times of day or different seasons of the year where different frequency bands work very well and where they don't work very well. And you can even pick up when a signal in its path, propagation path around the Earth's sphere, when it's following a gray line. So the border between daylight and darkness, either at sun up or sunset. And you get very interesting information from the WhisperNet database. And we're going to be putting out a few papers in the coming months on the IEEE antenna website. They have a subcategory on antenna and propagation. And we're going to put out a few papers on Wspr and how it works. So that would be interesting, and I can let you guys know the link when those papers are published. So
that would
Glenn,
be fabulous, by the way, Richard. Thank you.
Yeah. Glenn, I took the cheeky privilege of looking you up on QRZ. One of the things we do is we produce an antenna database. And why do we do that? Well, as you can see on QRZ, and there are many other websites used by radio amateurs, you get the call sign, and you will get in the WhisperNet database the Maidenhead locator. But a Maidenhead locator could be out by 5-6 kilometers either way from the real location. So, for example, we look people up. And Glenn has very kindly put his latitude and longitude in the database, and many others do the same, to 6 decimal places. So if that's correct, and I can look on Google Earth at that latitude and longitude and check it, but 6 decimal places tells me exactly where the transmission is to within a meter. Now, it could be that that's the latitude and longitude of your address, Glenn, but sometimes on Google Earth,
It is.
I can look up and you can see the antenna in someone's backyard. And then you can pinpoint it exactly. So rather than using the Maidenhead locator, which could be out by 5 or 6 kilometers, we use for the transmitter and receiver the exact latitude and longitude. Now, that helps enormously because with an ionospheric propagation, we got other fluctuations and tilts in the ionosphere. And every time you get a multi-hop propagation, every time it hits the Earth's surface, there could be a tilt. It depends whether an interim landing point is on the ocean or in a desert or in the Arctic ice or on a mountain. So we also, apart from the antenna database, we have a database of all aircraft. There are 25,000 aircraft in the air at any one time. And we have a database which gives us the exact latitude and longitude and altitude of the aircraft at each point in time. 75,000 in a day. That's a huge database. You need a very large computer to work out, did your WhisperNet signal from, I don't know, Greenland to Germany have an interim landing point somewhere near where an aircraft was? Now, an ionospheric propagation may be going up to 200, 300 kilometers above the Earth. So there are no aircraft up there, but there are aircraft at, say, 10 kilometers above the Earth. So every time a transmitter is near an airport or a receiver is near an airport, or the interim landing point in a multi-hop propagation is near an aircraft en route to wherever, we need to work out whether that is the reason rather than the target aircraft we're actually looking at. So it's quite a complicated elimination of, I don't know, 3 or 4 suspect other aircraft that are interfering with the radio signal. When you think about 25,000 aircraft in the air at any one time, you know, how often do you send a signal to someone, say, 3,000 kilometers away, that is an ionospheric propagation, but there happened to be an aircraft in the way at some point? Of course, an aircraft will move on, so that might just be a blip for a moment, and we get WhisperNet data every 2 minutes. And when you're tracking an aircraft over several hours, then every 2 minutes is quite a lot of data. We actually use a tool called PropLab Pro, version 3.2, to do ray tracing between the transmitter and the receiver. Do you guys use PropLab at all? It's a very useful tool for, you can put in the location of the transmitter, the location of the receiver, and you can do a ray tracing. So it shows where the signal goes up into the ionosphere, gets refracted back down to the Earth's surface. You can find out the interim landing points of that signal. You can see, for example, in this case, it does 1, 2, 3, 4, 5 hops before it gets to the receiver, which is at the black triangle. And in this case, 12,200 kilometers away from the transmitter. Oh. It's a very useful mapping tool. It uses the ionospheric reference model, 2007, and that only gives you the mean values for the ionospheric layers at different frequencies. So you tell it what frequency the signal was at, and you can find the maximum usable frequency. It can work out the elevation angle from the antenna and what the maximum elevation angle could be before it doesn't get refracted back. It just zooms off into outer space. So that's a very useful tool for us to do a validity check on any particular Whisper transmission and reception.
I have a question, Richard.
Sure.
This is 2007, right?
The reference
software?
model is from 2007.
Right. There, I've been studying a little bit about earthquakes and how severe earthquakes, 8+9, that sort of stuff,
Yeah.
can change land mass, can change the tilt of the earth and things like that. Is that significant at all in analyzing this data, these changes?
Yep, it is. And this PropLab not only has this reference model of the ionosphere, it has a topographic model of the Earth's surface.
Wow.
So
Okay.
if your interim landing point in a multi-hop propagation is in the Himalayas, for example, that can have a tremendous effect. If it happens to be on sheet ice in the Arctic, I mean, that's a very nice, relatively flat surface, and especially when it's ice over ocean. So jungle, for example, is difficult. Desert is better. Bouncing off an ocean surface, as long as it's not rough weather, and the ocean surface is relatively flat, is great news. And they actually give you different absorption rates and reflection rates depending on the frequency of your signal and where the interim landing point was. So some signals can go through over 10,000 kilometers or 20,000 kilometers quite happily. Others will, die a death at the first hop, so to speak. So it's a useful and interesting tool.
Well, it's very sophisticated, obviously.
Yeah, but it's only $99. So, and by the way, it's produced in Canada.
Oh,
So
there you go. Wave the flag.
You got some really clever guys there, and it's one of the best $99 that I've spent. What we do with all of this data is we build a statistical model called a receiver operating characteristic, which sounds complicated, but effectively what we do with every whisper signal is we work out the true positive rate of detecting an aircraft and the false positive rate. So at every point in the WhisperNet where we get an intersection of anomalous signals and say, okay, here's an interesting point, we do it when an aircraft is known to be there from the ADS-B data we download, and when we know there is no aircraft there. And we check, does Whisper get it right? Basically, does it tell us, yes, there is an aircraft when there is one, and it says, no, there isn't one when we know there isn't an aircraft? And the red dotted line is 50-50. So if you flip a coin, you would come out with the red dotted line. And what we come out with is not great, but a line which is definitely not 50-50 and following the red dotted line. We come up with the blue line, and we put on that the threshold values from the so-called 95% confidence intervals. And in most cases, those bars vertically are clear of the red dotted line. In some cases, not. But so it's a noisy sensor, and I wouldn't recommend it as a real-time, reliable radar. But when you consider it gives you an archive going back to 2008, and we can go into that archive to the 8th of March 2014, and we can pick out WhisperNet every 2 minutes for a 7-hour, 37-minute flight into the Indian Ocean, then what we do is come up with a flight path for MH370. The red dotted line is what Wspr tells us. It matches the Inmarsat data, those black circles, which I talked about earlier, come from the Inmarsat satellite, and it matches the fuel and the Boeing data on the performance of the aircraft. And surprisingly, the crash location, which is all the way down at 29 degrees south, matches the drift analysis of the floating debris that we found. And when you consider satellite data and oceanographic data have got nothing to do with radio data, they're all very independent analyses, and they all tie up, then we start to believe we've worked out the crash location of MH370. So that is basically what I wanted to communicate today. Do you have any questions?
So have they found the plane?
Not yet, but the Indian Ocean happens to be 75 million square kilometers and goes down to around 6,000 meters in depth.
Wow.
And they've been looking for 11 years, and they've spent $300 million US doing that. And so far, MH370 has eluded all the searches.
Wow. Wow. Is it the search is ongoing right at this moment?
No, they're not ongoing at the moment because it's the winter
Right.
months in the southern hemisphere. We're hoping they're going to go back in November of this year when the summer starts down there and things get a bit less nasty. The Indian Ocean is pretty nasty all the time, but in November it starts cooling down a bit, and the wave height is around 2 meters and not 4 or 5. So when you're trying to operate autonomous underwater vehicles or robots which you send down, called remotely operated vehicles, are sent down on a wire. Autonomous vehicles are sent down like a mini submarine. Handling all of that equipment and bearing in mind each of these AUVs or ROVs cost about $8 million each. So you want to make sure the crew are safe, and you want to make sure you don't lose any equipment in the process. But one of my co-authors is a guy called Professor Simon Maskell, and he is a scientific advisor to Ocean Infinity, who are the company who are planning the next search. And he is doing a study at Liverpool University into Wspr. He has the big computer to be able to track millions of aircraft. and he's tracking all the WhisperNet database for thousands of aircraft in a 24-hour period, in order to prove that Whisper works. And he was actually at the meeting in Malaysia where Ocean Infinity presented to the Malaysian authorities their current proposal for a search. And WhisperNet and what I've shown you guys, this particular location, 29 degrees south, is going to be searched hopefully at the end of this year.
Well, that's pretty darn amazing.
Yeah, and
Thank you.
it's all thanks to you radio amateur guys and the ones who have faithfully put millions of data into the WhisperNet database. So, you know, I take my hat off to you all.
Yeah. Any other questions out there?
No questions, just a
Okay.
big thank you for the intelligence.
Yeah. Thanks, Yvonne. Pierre?
Yeah, I have a
It-
question. The debris that was reported on the news that was found, does that enhance or match with your Whisper projection of where the flight went?
Sorry, what have they reported?
When some of the debris that was found,
Oh, yeah. Yes.
is that in your projected flight path?
Yeah. The debris, 43 items of floating debris have been found. Different locations around the Indian Ocean, from South Africa, Mozambique, Tanzania, and on the island of Madagascar,
Mhm.
the island of Mauritius and Réunion and Rodriguez. A good friend of mine, Blaine Gibson, has found quite a number of those, and he also motivated others to go look. There have been, meanwhile, about 20 different people who found debris, and what a number of eminent professors and clever oceanographic scientists have done is to try and trace where that debris could have started its trip across the Indian Ocean. And they have models of the Indian Ocean and the atmosphere and the sea at various layers, and very clever oceanographic models. And they can work out where the currents flow, where there are eddies, and how long it would take. A guy called Professor Charita Patiarachi from the University of Western Australia predicted where Blaine Gibson should go and look. And he said, Blaine went and visited him in Perth, Australia, and he said, Blaine, go to Madagascar. And Blaine said, well, my goal is to go to every country in the world, and I've been to Madagascar. Where else should I go? Mozambique. Oh, I haven't been there. All right, I'll go to Mozambique. Where in Mozambique? There's a long coastline. He said, you go to Vilanculos, and then you ask the local fishermen to take you out to the Paluma sandbank, and there you will find drift debris turning up. So he did that, and it took him 3 days, and he found an item of debris called No Step because it had written on it. It was a piece of the horizontal stabilizer from the tail of the aircraft, and it had No Step written on it. And it was quite amazing to me, you know, a scientific prediction of where to go look, and then someone who actually bothers to go look and then finds. Blaine has meanwhile found, I think, 7 items himself, and he's had about another 13 items handed into him. And in total, meanwhile, there are 43 items. There are probably hundreds still out there, but meanwhile, probably buried in sand or carried back out to sea, or I don't know. But it's a fascinating exercise doing a drift analysis with the oceanographers.
And there are some videos out on YouTube with that, with Blaine, I believe. I know I've seen at least one, which was
Yeah,
fascinating.
I do a YouTube video every day with a guy called Jeffrey Thomas on Daily Airline News, and we've done about 100 videos meanwhile, and some of those are with Blaine Gibson. There are a set of 4 videos just on Wspr, but we cover all aspects of MH370. Yeah, meanwhile, we've got over 2 million views of these videos, so they're quite popular.
That's great. That's great. Any other questions? Brian?
Yes, Richard. Well, first I was away for a few minutes. I'm doing some tests on 60 meters, and maybe I missed it. But in terms of all of the Wspr work, of course, Wspr, people are using Wspr, throughout the HF spectrum. So when it came to this particular exercise, were there any particular HF Wspr frequencies that were being used as part of the exercise to try to find out, or to prove the flight path and where it went down, or just one HF frequency? How was all
Well,
that addressed?
we had a problem with some of the experimental Wspr. So the vast majority of the WhisperNet database are between 3 megahertz and 30 megahertz. So, but
30, 13?
From 3 to 30. I mean, it's
30, right, right.
Yeah, 28, I think. But there are people, for example, who do 100,000 hertz, so 0.1 megahertz. There are people who do 144 megahertz Wspr. We have no problem with the lower frequencies, but we do have a problem with the 144 megahertz experimental data. But we use all the data between 1 megahertz and 30 megahertz on the WhisperNet database. And the great advantage of multi-frequency data is that you're not so dependent on the season of the year, the space weather, the solar activity, the time of day, and it gives you a much broader data set. So if it doesn't work on one frequency, it might work on another. And we're talking about trying to pick up aircraft in the Indian Ocean. So sometimes you get a guy in the Middle East transmitting and a guy in Australia receiving, and you need to know what time of day, what frequency works the best. So we use all the data we can get hold of, basically.
Okay.
Great. Any other questions? I was just thinking about next November, Richard, with the Infinity. What was that group?
Ocean Infinity is
Ocean Infinity, right.
the company.
Yeah, so I would be really excited to find out that, in fact, they found the wreckage, and we'll have to get you back on on Zoom here at Island HF. It would be sort of cool.
Yeah, that would be cool, and I'd be glad to join you once it's been found. And
Yeah,
if they find it where Whisper's predicted, then it'll be even more interesting
Yeah.
discussion.
Let's hope.
yeah, yeah. Okay, one final call out for questions. Any questions? Zach.
Richard, has Joe Taylor changed his mind about Whisper being used for tracking aircraft now?
Joe Taylor says, I think the guy is 85 and long since retired.
Yeah.
He still has an interest, of course. If you're a professor and a Nobel Prize winner, and you've been in scientific fields all your life, you don't lose that interest. But he basically says, I don't have any time for this new stuff, and I'm not interested. Christian Ensfellner, the chairman of the German Radio Society, who I showed the picture with Joe Taylor earlier, tried to contact Joe because they're personal friends, and offered to set up a meeting with people like Professor Simon Maskell and myself. And my other co-author is a Dr. Hannes Kurtzi from South Africa, who has a PhD in radio engineering. And unfortunately, Joe Taylor declined. So I respect his privacy. I guess when we start publishing academic papers in the IEEE antenna and wireless propagation officially, then we'll get a lot more. There are, meanwhile, I offer the software that I've written, and there's one YouTube video where I do a live demonstration of how that works to pick up an aircraft and track it.
Did you send that link to Richard?
Yeah,
that
sure.
possible?
Yeah, that's one of the daily airline news ones. But
Yeah.
yeah, I'll send you a link. I can also, by the way, I'll send you a PDF with the slides, and I have a PDF with the script for tonight, that I was sort of trying to follow in presenting. So you can put that out.
That'd be great.
To your members. So there are a number of academics who have taken up our offer of having a download of the software. You need a MATLAB license, and but there are many scientists who use MATLAB as software for their research and do have access to a license. And I invite people to try it out for themselves, because that's how I started. I tried it out for myself, and I can understand people are skeptical until they have tried it out for themselves. And more academic papers are being issued now on the subject of using Wspr. I mean, in effect, it is another form of passive radar, just like a over-the-horizon radar. There are some which don't rely on a transmitter. They just rely on all the signals that are out there. So GPS signals from satellites, or TV stations, FM broadcasts, and of course, all the radio amateur signals. I mean, there are over 3 million radio amateurs around the world, and they're not on the air all the time, but a lot of the time, and there's a lot of signals going out all around the world all the time. There was actually a paper, a NATO paper, written back in 2006, suggesting that a form of passive radar, which could be used for early warning system, is to use radio amateur signals and to use them as illuminators of aircraft, and pick them up like a radar system. So I think this will gain ground over the next few years quite significantly.
Andy.
Yeah, just one thought. I wasn't going to mention this in case it's too goofy, but I'm an amateur radio operator, but I was a professional radio astronomer and looking at events like stellar flaring. And it occurred to me that most of what's happened in the sky we don't detect because we don't have antennas looking at them. But there may be also radio flares on objects, if they're bright enough, might have effects that could be picked up by the Wspr system as well. So I don't know that my brain still works well enough to figure that one out, but that's what I'm thinking at the moment.
Well,
interesting.
If you go into all of the dynamics involved, so you mentioned solar flares, but there are so many dynamics, and people will note what the solar flux index is, or the KP index is, or but there are more and more studies being done on understanding how radio waves actually propagate. And what we're doing in a way is sort of ironing out the fluctuations by using the results over a longer period of time. And Wspr is great because it uses this integration over 110.6 seconds. And that is a so-called coherent integration time. Now, in 110.6 seconds, the ionosphere will also fluctuate. But if you integrate over 110.6 seconds and then do that again every 2 minutes, you can smooth out statistically and be able to literally pick the signal from the noise, and then detect and track an aircraft. It's a complicated process, but it's not impossible.
Thank you. Thank you.
Anyone else? We got Richard here. Take an opportunity to ask him a question.
Well, if you come up with a question tomorrow or
Yeah.
next week, that's also fine.
Yeah.
Glenn, so, you know, just let me know and I'll do my best to answer.
Absolutely. We'll keep in touch. This has been absolutely fascinating. And we'll make certain the members are aware of the location and yourself, the location of the video. And yeah, hopefully we can get together again and talk about this. It's been fascinating. Thank you very much, Richard, for taking an hour and 7 minutes or so here to chat with us. It's been delightful.
Well, sorry for the 7-minute overrun, but never mind.
No.
But
Okay.
don't forget to send me the link to your YouTube recording.
Absolutely.
Yes. I'll start it, but it takes about a day or an overnight anyway for it to be posted.
I know YouTube is difficult and takes a long time sometimes to get it downloaded and then edited and then uploaded and so on. And they want to check any copyright violations and what have you. So it's quite a rigmarole, but whenever you get it, send me the link. I'll be interested to watch. And yeah, Glenn, we'll stay in touch.
You bet. Thanks again, Richard.
Yeah,
And
thank
thanks
you.
everybody else for joining us today. It's great to see you all again. And possibly you have, with your Wspr signals, have helped Richard find
Oh, yeah,
MH370.
indeed. Thank you
Okay.
very much.
Reigniting my desire to get back on Wspr.
Yeah.
I haven't done it for about 4 years, but yes, it really
Yeah.
piqued my interest.
Okay.
Okay.
Fabulous.
Richard.
Thank you.
Thank you
Thanks,
very
Richard.
much.
Okay.
Thank you.
Bye-bye.
Bye for now.
Bye, everyone.
Bye-bye.